Hello, I'm just going to go through the GCSE Physics paper 1 from May 2018, question 5. Press play and pause as you wish and go through the answer in your own time. Question 5.1. Complete the sentence. Choose answers from the box. So the current through an ohmic conductor is directly proportional to the something across the component, providing that the something remains constant. So let's just go through what we mean by ohmic conductor. Well, any conductor is something that conducts electricity, and if it's ohmic, the clue there is that current and potential difference are directly proportional. What that really means is, if you plotted it, you'd get a straight line, and the resistance therefore does not change, so the resistance is constant. So the current through an ohmic conductor is directly proportional to the potential difference. Now, something that changes the resistance is temperature. So in order for something to be ohmic, you need to make sure that the temperature remains constant. The hotter something is, the more the particles will vibrate. And the faster they vibrate, the harder it will be for the electrons to get past when they're in the wire. So the lower the temperature, the lower the resistance. The higher the temperature, the higher the resistance, just because it makes it harder for the electrons or the current to flow. In question 5.2, figure 7 shows a current potential difference graph for a filament lamp. Explain how the resistance of a filament lamp changes as the potential difference across it increases. So let's look again at our axis. So we've got the current, so that's how quickly the electrons flow, and the potential difference, and that's the push. So the harder the push, the faster the current will generally flow, assuming the resistance is the same, and that's what this graph was saying here. So we can see that for a small increase in potential difference to start with, the current increases by a large amount. However, the curve is starting to flatten, and what that means is even if we increase the potential difference by quite a large amount, the current doesn't really increase by much. So because the current can increase really easily here, we say that there's a low resistance. And here, because the current doesn't increase as easily, that's because there's something opposing the increase, and the thing that's trying to slow it down is the resistance. So the current does still increase, but by not as much, because the resistance is that much stronger. So if we go back to the question, now we started to plan our answer, what we can say is the current increases when the potential difference increases. Now the only problem with that sentence is that that's true of a straight line graph as well, and we don't have a straight line graph, so we need to articulate to the examiner, it's worth 3 marks, that we haven't got a straight line, that we've got a curve. So we need to add to that. So we need to link the idea to the temperature changing and also how the resistance changes. So let's show that the resistance is increasing. So to start with, the resistance is really quite low, and then as the potential difference increases, the resistance gets higher. And then the reason for that is because, well, we know with a filament lamp, they get hot. And we've mentioned earlier that when things get hotter, the resistance goes up. So this is because the lamp is getting hotter, and then that makes it harder for the electrons to flow as easily. For the next question, 5.3, many householders are replacing their filament lamps with LED lamps which are more energy efficient. What does energy efficient mean? So something that's efficient, it means there's less wasted heat in this case, or less wasted energy in more general terms. Or you could say there's a higher proportion of energy that is usefully transferred. The whole point of a lamp is to give you light, and what you don't want it to do is produce heat energy. So what does more efficient mean? So I would say something like there's a higher proportion of energy that is usefully transferred. Moving on to the next page, a light-dependent resistor, or LDR, is used to turn on an outside lamp when it gets dark. Part of the circuit is shown in figure 8. So what do we have in figure 8? Let's just have a quick check. So we've got a 12-volt battery, we've got a resistor of 2000 ohms, and here is our LDR. Now what I also notice is we've got some lines going off here to an outside lamp circuit. So this bit here is in parallel. Anything in parallel will have the same potential difference as the thing that it's in parallel with. So whatever the potential difference is here, the potential difference will be the same just here. So keep that in mind. So question 5.4, the light intensity decreases. So I'm not going to read anymore. I need to now remember a graph. And one of the graphs for an LDR looks like this. And it tells us the resistance against the brightness, or the amount of light that there is. So in other words, when it's bright, the resistance is low. So bright equals resistance low. And when it's dark, that means the resistance is high. So in this case, we're looking at the light intensity decreasing. So I might just say getting darker. I'm going to read on. What happens to the potential difference across the LDR and the current in the LDR? So we've got to remember there's a link between resistance and potential difference. If the resistance goes down, that also means the potential difference goes down. And if the resistance goes up, that means the potential difference goes up. The reason being, if the resistance goes up, that means you need to increase the push to keep the current the same. If the resistance goes down, you need less of a push, which of course is our potential difference, how hard you're pushing the current around the circuit. So for question 5.4, because it's getting darker, that's this one, the resistance is going up, so therefore the potential difference is going to increase. And likewise, if the resistance is going up, that makes it harder for the current to flow, and if it's harder for the current to flow, the current will decrease. In question 5.5, what is the resistance of the LDR when the potential difference across it is 4 volts? Give a reason for your answer. So let's find the LDR again. So that's just here. And we know that voltage or potential difference is 4 volts. In a circuit, if we start with 12 volts, 4 have been used here. That means 8 of them have been used here, because the 8 plus 4 gives you the 12. So we can see a ratio here that there's double the potential difference, which equals 2000 ohms. This is half the potential difference, so this one must be 1000 ohms. So the resistance is 1000, and the reason is the potential difference is shared in proportion to the resistance. For question 5.6, calculate the current through the LDR when the resistance of the LDR is 5000 ohms. Give your answer to 2 significant figures. So in each test paper, there'll always be a question asking you to give your answer to a certain number of significant figures. That's going to give you 1 mark. So the resistance can change of an LDR depending on the brightness. So now it's changed to 5000 ohms. And we're asked to find the current. So we know that the potential difference, the total potential difference, is 12 volts. We don't know what the current is, but we do know the resistance. Now it's the resistance of the whole circuit. So the resistance of the whole circuit is now 5000 plus 2000. So that's then 7000. So we know an equation, potential difference equals current times resistance. We want to find the current, so current equals V divided by R. V is 12, R is 7000, and that will give us the current flowing through our circuit. So then if you put those numbers into a calculator, that will be 1.71 times 10 to the minus 3, or 0.0017 amps. That brings us to the end of question 5. As ever, if you have any questions, please let me know.